Okay. Okay, we are in the last chapter of this quantum mechanics course, which is devoted to what is called central potentials, and in particular the hydrogen atom. Maybe let me summarize this chapter 5, just the structure that was a little bit here and there, right? So we are in the chapter 5 is quantum physics in 3D, and we saw a few things that are general, and a few things that are for the material point, specifically. So we started with the description of the state and operators of the material point, specifically, psi of x, and the operators x and p. This was chapter 5.1. Then we did something general on angular momentum. And I remind you that angular momentum is defined by these commutation relations plus the cyclic permutations. Then we specified angular momentum for the material point with L equal x cross p. Before that, we specified the angular momentum for the spin half. It was a special case. And what we saw is that this fellow, there are these famous quantum numbers J and M, and here there is L and M, and here J can be either integer or half integer. Here L must be a natural number. So integer, sorry, yeah. Here can only be an integer number. And now what we are going to do is to stay on the column of the material point and to consider Hamiltonians h p squared over 2m plus v of x, where v of x has a special form that is a central potential. So let me define a central potential here. So this is central potential. This means that v of x is actually only a function of the length of the vector with respect to a reference point, which in spherical coordinate we would write v of r. So in other words, this in principle is in spherical coordinates v of r, theta, and phi, but actually is only a function of the radial coordinate. And let us see what that means. So I erased the summary. I think you have the map now of the chapter. And let me rewrite the Hamiltonian for a central potential. H equal to p squared over 2m plus v of x. Now, without calculation, it's manifest that this Hamiltonian is invariant by rotation. Why? Well, because the norm of a vector is invariant by rotation. And the Hamiltonian, there is a function of the norm of the vector p, p squared, plus another function of the norm of the vector x. So upon rotation, these will not change, that will not change. Therefore, the Hamiltonian is invariant by rotation. And as explained in the previous lecture, in general, something that is invariant by rotation commutes with the angular momentum. In this case, since this is a material point, the angular momentum is L. So this immediately implies, if and only if, H commutes with L. And I remind you that this commutator between a scalar operator and a vector operator is a convenient way of writing that H commutes with all the components of the angular momentum. Now, this can be really, if you don't trust me, this can be really computed explicitly, right? You plug in the expression of H, you plug in the expression of L equal X cross P, you start computing commutators, and you will find that it's 0. And it can be done, right? Maybe it's a very useful exercise for you to practice the algebra of infinite dimensional systems and the commutators and everything. But this argument, once we know that this object is the angular momentum associated to the material point, the fact that something is invariant by rotation is if and only if that something, in this case the Hamiltonian, commutes with the angular momentum. So I will leave it there. I will not do this proof in a calculatory style. Okay, so now we know this. What is our goal? As usual, all right, we have Hamiltonian. We want to find the eigenvalues and the eigenvectors. Because if we find them, we find the dynamics. So the goal is now solve H phi is equal to E phi. And now I will use this. How do I use that? Well, because H commutes with L, we can find a basis of common eigenvectors of H and of, not of L, because the different L do not commute between themselves, but we can find a basis of H, L square, and LZ. So look for phi, that we will denote by phi KLM, such that these holds H phi KLM is equal to E of KL, not M, because of essential degeneracy, phi KLM. Remember, if something commutes with the Hamiltonian, its eigenvalues cannot depend on M. Then we also request that, sorry, not that H, that J square, sorry, L square on phi KLM is equal to H bar square L plus 1 phi KLM, and we request that LZ on phi KLM is equal to H bar M phi KLM. Okay, so that's the problem we want to solve. Why we can solve it again? Why can we hope to find these vectors? Because the Hamiltonian and the angular momentum commute. But then, actually, we have already solved these. These two, we already know what it is. It means that phi KLM is going to be a radial function, well, possibly depending on K and L, of R, times the spherical harmonic YLM theta and phi. Sorry, I've made a mistake here. This is not that vector, this is the wave function. In spherical coordinates, right? So I replace this x by r, theta, and phi, and we have already this form in x representation spherical coordinates for the state, and all that we have to find is what is this. This one is clear from that, right? So maybe you see now a little bit, at least in this example, the importance of all the work we did before. You may before ask, why are we doing all this work with the angular momentum? What are we trying to find out there and so on? Well, what we're trying to find is that once we have this kind of symmetry, like invariance by rotation, a lot of the problem is already solved by knowing the property of the angular momentum. So now, the thing that you have to do is, how does the Hamiltonian look like? So now we have the Hamiltonian, which is in X representation, right? We are in X representation, although in spherical coordinates. What does that look like? Well, it's minus h bar square over 2m gradient squared plus v of x. And if I pass in spherical coordinates, you can take your electrodynamics or the appendix of any book on things that have curls and derivatives and whatever to find how to express the gradient in spherical coordinates. I will not do it here. I will just write the result. It looks very interesting. So the gradient looks like this. There is the radial component is something like that. Maybe you remember this one. It's not too hard to remember. It's an operator. It's right. There is the function here. So you have to multiply your function by r, derive twice by r, divide again by r. And then there is something like this times some derivatives of d over d theta and d over d phi. And when you look what that looks like in your textbook and you compare with what we have done in the previous lesson, you find that those derivatives are exactly L squared divided by h bar squared. And then plus v of r. Okay? But now we have that function, right? We have to solve this problem with that function. So hx on f kl of r ylm on theta and phi is equal to what? Well, all this mess, but these L squared that are the derivatives on theta and phi, we know how it acts on these theta and phi, so we'll have minus h bar square over 2m 1 over r double derivative r minus 1 over r square h bar square ll plus 1 over h bar square plus v of r fkl r ylm theta and phi. So all that I have done here is to again use the fact that I know that the angular component is an eigenvector of L square for the eigenvalue h bar square ll plus 1. And now please allow me to erase something. I will erase the h bar squares. There's no point in leaving them there. And now you see that everything that is left here now depends only on r. So I don't need to keep track of the fact that there are these spherical harmonics there. Their role has already been realized. And here is what we want to solve. I will write it now here. E KL FKL of R. This is the famous differential equation to be solved to find the solution to our problem. It depends only on R. It's only a radial equation. This is a radial equation. Nobody claims that it's easy, but we have simplified the problem as much as we can. Given that we don't know yet what the potential is. All the rest is fixed. All the rest are just derivatives with given terms. These were still free. Now, before I go on, I will just write these things in a slightly different way to give a kind of intuition of what's going on with angular momentum. So if I rewrite the Hamiltonian in a different way, I can write it like this. Minus h bar square over 2m, 1 over r, d square over dr square r. And then what do I have? I have this thing. So I have plus h bar square L plus 1 over 2m r square plus v of r. That's the Hamiltonian. Now again, even if I'm very slow here, I remind you where this comes from. This comes from the gradient square the part with d over d theta and d over d phi. So this plus that was part of the gradient. But now it's a mathematical problem, right? So you can look, what does this look like? It looks like a gradient in R plus a potential with two terms. The term that is the normal potential and this object. What does that object look like? Well, if we do a drawing, this one, right, as a function of r. Well, it's something like this, right? And here it goes like 1 over r square. Of course, this is only for L larger than 0. For L equals 0, this term is 0, there's no problem. For L larger than 0, it goes to infinity at r equals 0. It means in a sense that there is, it's going to be, so whatever this term is, it will be very hard for the particle to go closer to the center. That's what it means. So if L is larger than 0, the material point will not be found at r equals 0, because there is a repulsive potential that keeps the material point away from, it's like a centrifugal force. Okay, so this is essentially the analog of a centrifugal force. And of course you have a centrifugal force only where angular momentum is not 0, right? If your angular momentum is 0, there's no centrifugal force. But if you are in an angular momentum non-zero, you feel this kind of centrifugal force due to this term. This is just for a kind of physical pseudo-interpretation, right? Now we are going to solve this problem exactly for a very specific case, which is a hydrogen atom. Okay, so let's keep in mind that equation. And let's concentrate on the hydrogen atom. I can probably remove these, yes. If you forget about this, you can still go back in the video and look at it. I will erase actually everything so that we have more place to discuss the hydrogen atom. So the hydrogen atom what is the hydrogen atom? Is one proton and one electron. And how does the Hamiltonian look like? Well, it looks something like that. There is the kinetic energy of the proton, and the notation should be something, well, okay, I used M1 and M2 in the lecture notes, but let's go physical, right? Then you have the kinetic energy of the electron, and then you have the Coulomb potential between the electron and the proton, which is something like minus q squared over 4 pi epsilon 0, 1 over the position of the proton minus the position of the electron. Now you say, well, but this doesn't look like exactly a central potential. How comes? Now this is getting very confused. There are two objects here. There are the difference in positions. That sounds new, right? And maybe we need tensor product to solve this. Indeed, we need tensor product in principle. But you know from classical mechanics that any problem of this type, and in fact, what I'm going to do is independent of what this potential is, as long as the potential is like that. These can be transformed into two separate problems, the center of mass and the relative coordinate, right? So if you define the center of mass coordinate as being the center of mass, and the momentum of the center of mass is just the sum of the momenta. And then, of course, you have to define 2 degrees of freedom, right? We had 2 proton and electron, 2 particles, where we need to do 2 degrees of freedom. One is center of mass, the other one is relative coordinate. And the momentum of the relative coordinate then you plug all these things in there. I'm sure you've done it in classical mechanics. I will not do it again. And what you find is that the Hamiltonian is going to look like that. I will write it here for reference. The same Hamiltonian in these variables will look like H is equal to the momentum of center of mass square over 2 the total mass, plus the momentum of the relative particle square times 2 what is called the reduced mass, plus the potential that we had there, function only of these, of the length of the relative coordinate. So what do we have here? Exactly like in classical mechanics, we have the center of mass is a free particle, and the relative coordinate is a central potential. And now what we are going to study is this Hamiltonian. So, because the proton, for the hydrogen atom, sorry, we're going to study this for the Coulomb Hamiltonian that is usually written like that. Where R is this, and E square is a notation for that. Okay? Now, because the atom is typically 1,800 times heavier than the electron, so the proton is 1,800 times heavier than the electron, it's like the sun and the earth. Well, the sun is much more massive than the earth. You can say that this is the electron and this is the proton. But there is a small change, right? It's exactly like the earth and the sun, right? In principle, you can say that the earth rotates around the sun. Technically, both of them rotate around their center of mass, right? It's exactly the same operations that have been done here. So, in summary, what a quantum mechanics textbook calls the hydrogen atom Hamiltonian is the Hamiltonian that I've written there, that I write it again now without R's. So now the goal is to solve, the goal is always that, but in practice we are going to solve for these. So we're going to solve minus h bar square over 2m 1 over r d over dr r square minus l plus 1 over r square minus e square over r, the whole thing, f for psi kl r, let's call it f, let's go, why not, is equal to e kl fkl of r. And the interpretation is almost electron in the presence of the Coulomb potential of the proton. That's what is called hydrogen atom. Okay. And now, since we are all tired and we are coming to the end of the year and we've already covered a lot of material in this class, I come with the good news. I will not do the solution explicitly. I just give you the result and comment on it. Those of you who want to see the solution in the course Atomic and Molecular Physics 1, PC2130 I think, Kai Diekman does the full solution of this thing, because of course the hydrogen atom is the starting point of atomic physics. It's, needless to say, in every textbook, so those who want to really be sure that what I'm going to say is based on solid mathematics can follow those developments, but I will not solve this equation for you, I will just give you the result. Okay, and so we can leave it there. Let's go a bit qualitative first. So what are we going to have? The Coulomb potential, this one, minus E square over R, is obviously something like this. So, well, this is a radial coordinate, is not a x, so it doesn't have the negative things, but the same ideas that we had for the piecewise constant potentials kind of apply in general, is that this equation will have continuous spectrum above 0. So every energy larger than 0 is a possible solution. And in this case, we get the same as for the potential, for the piecewise constant potential. These are diffusion states. And if you want, you have to decompose on them. So electron that escapes the attraction of the nucleus. In other words, ionization. Okay? If a particle has an energy larger than zero, if the electron has energy larger than zero in this system, it means that the electron is not confined anymore by the potential of the nucleus and is escaping. I must say, however, that this is a long-range potential, so the description of the diffusion states is very, 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 very difficult. Because even at a long distance, because the potential decreases very slowly, you still see some effect. So the description of the diffusion state, very advanced topic. And that's all that I'm going to say about the diffusion states. So that's it. Now we have to look what happens. Are there energy levels here? Here, the particle is bounded, right? You can imagine this is it has a spherical symmetry, spherically, by the way. I'm just doing it as if the space was two-dimensional, actually it's three-dimensional. So here, if an energy is below zero, the particle is kind of confined. From the theory of piecewise constant potential, we expect here to be discrete energy levels. And indeed, that's what we're going to find. I will just erase these comments on the diffusion states. You just keep in mind that there are diffusion states up there. Below here, we have discrete levels. Now, I should try to space them in a decent way. How they are spaced? So the first level, let's call this energy E1. And E1 is a number that everybody remembers by heart for some reason, is 13.6 electron volt, is the ionization energy of the ground state of the hydrogen atom. Below, there's nothing. Now, the nth level, En, is E1 over n squared. So in other words, this one would be E1 over 4. Remember, E1 is negative, right? So if I divide by 4, I go higher. This one would be E1 over 9. Obviously, my scaling is wrong, right? Because 1/9 of this scale should already be here. It's just that I wanted to show a few more levels, right? So the third energy level, n equals 3, is already at 1/9 of this whole scale, and so on. This formula is another one that you should learn by heart. So the nth energy level of the, of course, n here is not 0, right? This is the thing that I didn't solve for you. Now what is n? Here I had a KL, and here I had a n. Well, the K and the L that are defined in there are related to n in the following way. En is equal to E1 over, I will tell you what that means, K plus L square, for K natural non-zero. And L, of course, is whatever L it is. Okay, but what does that mean? Okay, what it means, and this is very important, you have a tutorial to do that, but I will spend some time doing it myself, is that these levels have some degeneracy. Let's look for it. Let's check E1. So E1, I need K plus L equal to 1. But K cannot be 0. Must be at least 1. And L, remember, cannot be negative. So the only possibility to get that is that L is equal to 0, and then K is equal to 1. If L is equal to 0, there is M is also equal to 0, and therefore the ground state, there is only, if I write it phi K L M, this would be phi 1 0 0. And if I write it phi N L M, which is the usual notation, by the way, also will be phi 1 0 0. So not degenerate, only one state. Let's check for E2. Well, E2, I have two possibilities for L and K, right? I can have, if I have L equal 1 with K equal 1, or I can have L equal 0 with K equal 2. If L is equal to 0, there is only the M equals 0 state. But if L is equal to 1, M can be minus 1, 0, or plus 1. So there are 4 states with E2. In the notation, from now on, I'm using only the notation with N here. We can have phi 2 0 0, phi 2 1 minus 1, phi 2 1 0, phi 2 1 plus 1. Okay? I repeat, there are the energy level E2, sorry, this one, is 4 times degenerate. There are 4 independent orthogonal states that have that energy. How they differ from each other? They differ by angular momentum states, not by energy. Of course, they're in the same energy level. Now, if you want to do the same exercise for E3, and you will find 9 states. You will find the 0 0, the 1 M, and the 2 M. Here there are 1, here there are 3, and here there are 5. And so on. And there's a tutorial there where you can really play with this degeneracy until you get really bored and you understand how it goes. Okay, now last point that I want to make is about the bound states. How do the eigenvector look like, the wave functions. We know already the radial wave function is going to be a spherical harmonic, well, with those numbers, right? But how does the radial wave function look like? Okay, I will write it here. The radial wave function f k equal 1, L equal 0 of R, that would be, in other words, the f n equal 1, L equal 0 of R. This looks like this. And so if I plug in also the spherical harmonics, remember that the spherical harmonic for 0 0 was just a constant. We have the beautiful phi n equal 1 0 0 of x now, that is equal to 1 over square root of pi a0 cube e to the minus r over a0. So this is the wave function of the ground state of the hydrogen atom in all its beauty. You see, it's invariant by rotation, right? So, which means independent of theta and phi, and that the radial component is exponentially decreasing, something like that. But because L is equal to 0, possible to find the electron at r equals 0. In other words, the electron on top of the nucleus. Because remember, if L is 0, we don't have this centrifugal force. We just don't have the screening potential. And then, just for your horror, I can write what the radial wave functions look like. Actually, I will not write it because it's written in the lecture notes, and honestly, there's nothing nice there. But I will just tell you what the structure is for the radial wave functions in higher, for higher states. There is a tutorial where you can practice some of these things, and of course, if I ask something like that about in the exam, I will give you all the functions, and then you compute all the integrals, right? That's as things go. But just to have an idea, I should not erase the potential, but anyway, I will write it again. So the radial wave function looks like this. The radial wave function f of, now I write n instead of k, but you know that n, this is equal to k plus L, so you can find the k from knowing L. Is something of this type. There is r to the L times a polynomial of degree, what is it, k minus 1. The whole thing here can be seen as a polynomial of degree n minus 1. And now this guy times e to the minus r over n a0. So what does that look like? Well, again, qualitatively. Let me redraw my potential. We had, let's say, Coulomb potential. The first ground state is just an exponential. So at this energy here, we have just something that does this. Now, the other ones will be different polynomials of degree n minus 1 times an exponential that goes faster. Now, these different polynomials, let me write them, two of them here. So this, for instance, is n equal 2, right? This is e1 over 4. This time I'm not too bad in the splitting. There are two cases there. You see that L comes in front, right? If L is equal to 0, is something that looks like that. Yeah. There is one oscillation, and then goes like this. This is for L equal to 0. And for L equal to 1, it will be something that is, so L equal to 1, it means it is 0 in R equal to 0, so it sounds like that. And then it will be something like this. And then, okay, if you have a higher n, you have a lot of oscillations. So now I'm going to do a completely crazy drawing that has no sense apart from pedagogical idea. If you have any n, you have a lot of oscillation while you are here until you get out, and then you go down with a very quick exponential. You see the exponential depends on n. So as soon as you go out of the well, essentially you die out. Okay? So that's, roughly speaking, how the eigenstates of the hydrogen atom look like. Okay, one last remark. You have some examples of this in the tutorial, but what are the average position? So here you have to be a bit subtle, right? Remember that R is only positive. So it's a little bit, so the average position, total position, on any eigenstate, remember this is an eigenstate, huh? Is 0. So the average position of the electron around the nucleus is always at the position of the nucleus, of the proton, for every NLM. Now, what is the average R? So the average R is not the same as the average X, right? The average R is somehow, because R is square root of x squared plus y squared plus z squared. And obviously it's a strongly nonlinear function of x, y, and z. So the average R turns out to be, depends only on L and NLL, and is something that is not too far from n squared of A0. So this A0, called the Bohr radius, by the way, I should have mentioned it before, it's something that somehow quantifies where is the average of these wave function. Okay, so with this, however maybe anticlimactic it is, we have finished our quantum mechanics 1 lesson. So I covered all the material that I wanted to cover. I told you at the very beginning that the syllabus of this module is objectively very, very heavy. And that is why I decided to skip a few things towards the end. In particular, in this lesson, I skipped one of the big traditional topics, which is the explicit solution of the hydrogen atom problem. But I think we've got enough physics by now. At least you have an idea of how hydrogen atom looks like. Again, you have some tutorials to practice some of these wave functions in spherical coordinates so that they don't look completely foreign to you. With this, I thank you for your attention. I'm very sorry, probably you too, that the current situation has forced us to do these things by video. But that's how it is. Some of you, I think they are happy because my accent and my speed are sometimes very unusual, and you can now pause calmly and listen to me again. Well, if that's a pleasure, why not? And, well, I will see you for the Viva and for the final exam, and I hope to see you more often, maybe in the following years, in the corridors of the physics department. Thank you very much.